Hello, my name is Benjamin Smith. I'm a current junior in JEG high-powered rocketry. I am the current vice president for the 2025 to the 2026 school year. I've been doing high-powered rocketry for 3 years now, with myself working on my level 3 certification. This is going to be the starting YouTube tutorial on how to become certified in high-powered rocketry through HPR. There's going to be 4 videos, with one being design, one being approval, one being manufacturing, and then finally the launch. This is the beginning to the design video, where we're going to be starting to look at components of a rocket. So right over here, we have a high-powered rocket. Shout out to Raymond, who is the current president, to donate this rocket to show us what components of the rocket are. So we'll start at the top. This is a nose cone that leads directly onto the nose cone outer side, and then the shoulder, which slides into the payload section. On this tutorial, I will show building a rocket with a payload section. So with a payload section that goes directly into here, where a payload section will be where you can put anything, including electronics, plushies. I put an egg in there. Someone told me if an egg can survive flight, a human can. So food for thought. You can throw cameras in there to record your launch. That will be a payload section here. That leads directly to the coupler. Its job is to mate with the two outside body tubes together, where itself will be connecting these two together. On that, there is a bulkhead here, which was where the eye bolt is attached to, and that goes straight to the shock cord. For our tutorial, I'll show a quick link as connecting to a eye bolt to shock cord. There's pros and cons to this. I like to do this where I can change out different components of my rocket. That leads directly to the eye bolt, which is this, which holds on to either a bulkhead like this, or a section ring like this, where the quick link will just attach directly on, and then you'll screw it on to connect. So after that, we have the shock cord, which itself is where the parachute gets attached onto, which I'll show later in this tutorial. But also, more importantly, it holds the rocket together on the descent from apogee in flight. So, carrying on to the booster side of the rocket here, where we can see the fins on this rocket, with it being a 3-finned rocket, as well as the rail buttons here, which holds the rocket onto the launch pad before flight. Now, inside of here, we have our centering ring here, with the first one having this eye bolt to connect the parachute, the shock cord to. The second one being here, where we have 2 in-sync screw sets where we attach motor retainer hardware, as well as for our L1 certification, a motor adapter, which itself will be slid into the inner tube where the motor sits. This allows you to fly with a 38mm motor on this rocket. And then for your level 2, we use a J250, well, it uses a 54mm inner tube. So now with this little rocketry introduction on what components are, we can start the design phase, where you will meet me in the annex, one of the computer labs in engineering. Okay, hello. This is the annex. Well, behind the wind tunnel of the annex. The annex was a little busy and a little loud, so I switched back here. So first we're going to start off with opening up Google Chrome, and then going to Open Rocket. as well as then downloading it. So go down to downloads, click download. For Windows, I recommend this one. Depending on the chips that you have to go with the sort of downloads. I already have it downloaded on this computer, so we can just open it up here. Little disclaimer, these dimensions I'll be talking about is based off of the dimensions that we'll be using for the 2025-2026 school year, as well as limiting factors that we have for manufacturing. So with that being said, we have two different types of body tubes that you can manufacture for your rocket, a 4-inch body tube and a 2.5-inch body tube. We recommend a 4-inch body tube just because it is a safer build itself. But you have benefits with it having higher payload section, and then for the 2.5-inch benefit, it goes high fast. Itself has higher risks because of that, so we recommend the 4-inch body tube when you're getting certification. But if you want to do that after the certification, it's up to you. But a little tour of Open Rocket. On the bottom here is the visual of the rocket. Here on the left is the rocket tree where you can see the components. Here is the new components you can add on to, as well as the rocket design, motor and configurations, which we'll get to in a little bit, as well as the flight simulations again later in this video. We have the file, we have the editing tools and preferences and scales, we have our tools, we have our help. For right now, I'm an imperial type of guy, so I'm going to be changing the preferences of the material of the units to imperial, and then changing the velocity to miles per hour and acceleration to G's and mass to pounds. It just makes sense in my head for these units, but if you like metric, make it in metric. So just like in the video in the lab, or part in the lab, we'll be starting from the top down. So we're going to be starting with a nose cone. This pop-up here is for if you have a kit. If you're making a rocket in HPR with materials that we have for building a rocket, it'll be a scratch built, so we'll just close all of these tabs so it's not needed. But if you do buy a kit, each number will have a part number, and you can punch that into here, and it has all the dimensions. You don't have to make a new part for it. So, on to actual manufacturing. So, biggest limit on the nose cone is the length. Our printer can be 10 inches, or if you want to be a little difficult, I'll be showing that way. You'll be making multiple types of nose cones, with them being with it being like segmented, with having a base and then the actual nose cone. So that itself is a lot harder to do, and itself is more complicated. I'll be doing that to show how to do that for people who want to do it that way. So for materials, this will be 3D printed, so we're going to be finding PLA in this. It'll be under the plastic section on probably the updated version. The base diameter for a 4-inch body tube is 4.125, as well as the length. I'm going to be doing a 3:1 ratio, 3:1 ratio. So that just means the base diameter times 3. So I have 1 diameter per 3 length of that diameter. So it's 4.12 times 3. Open Rocket, you can do basic calculations in there to get conversions, or what you can do is change the actual unit for that one part. It will reset back to your unit that you saved actually in the edit. So if I change this to be millimeters, put in millimeter numbers, come back to it later, it'll be in inches. So thickness of this is 0.2. Onto the shoulder. Shoulder, you want roughly a 1 diameter per 1 length of length of the component for a friction fit for a rocket. So with this being a 4-inch body, we want around a 4-inch shoulder. I'll be going with a 3-inch. That's on the low end, so I'll be going 3-inch. The thickness of this will be 0.2 inches, and then the diameter of which will be 4 inches. So our inner dimension of our body is 4 inches. So now with that, I'm going to be jumping over to make sure this is all good. Now the nose cone is complete. We can go on to the body tube. Again, close out that pop-up. Inner dimension is 4 inches. This will be a cardboard material. Your total length of your body tube that you get is 37 inches. So you can use all of it, none of it. If you want to pay a little more, you can get another tube. But this section will be, for the payload section, I'll say 17 inches to allow for a 20-inch section down at the base for the motor. Now with that, I'm going to be relabeling the component name to payload section or payload tube. And then with that being done, we can finish out of there, and we can add a tube coupler in the inner components section. Close out of this, the thickness of which is 0.2, just like all the other 3D printed components, of which it's PLA. And then for the thickness of this, we want to be at least around 8 inches, with it being 2 lengths of a friction fit. So I'm going 6 inches, just because I'll be epoxying the upper end of that. So that's going to be here. I'll make that 6 inches. And I'll be moving this forward to have to be plus 3.5 to allow for almost 4 inches on the friction side, and then 2.5 to 2.5 inches on the epoxy side. And then with that, we can close that out. Onto the bulkhead of this. The thickness for the wood that we have currently is 1/4 inch birch. So I'll be making this to birch. There we go. And then we'll be pushing this back 4 inches to allow 1/2 inch or 1 inch of length in our manufacturing process to allow us to not have it up against each other. And then we're going to add a mass component to account for the eye bolt as well as the quick link that I showed in there. Now this is an example of us changing over to grams, the weight of which for both of them is 40 grams total. It's going to be 1/2 inch length. I'm going to change that to the bottom component. So if I bring it to 0, it goes to the base of the parent component. And I'll back that up 2.5. And then if you have a payload section, you'll account for the mass in here by adding a mass component and then making whatever dimensions it is, and then the weight. I'm currently not having one simmed in this rocket, but you are open to have that in there. But it's nice to have that section in there to future-proof the design, where you can have cameras, electronics, plushies. Like I said in the lab, I had an egg in my L1, and in my L2 I had 2 eggs. But it's up to you to decide. Past this section of the body tube, we are complete, so we'll move to another body tube. This will be the motor tube, where the motor body tube section, where the motor will be located. We use 17 inches on the payload section, so that leaves 20 inches left over for the motor section. And again, our inner dimension is 4 inches. It is cardboard, and there we go. So now to work on the internal sections of this, we are going to have a inner tube here, of which the length is 10 inches, a outer dimension of 57 millimeters, and then an inner dimension of 54 millimeters. Now, the benefit of this design, it allows for the all uses of 54 motors, as well as using an adapter, which will account for its mass for our level 1 design and level 1 launches. So this will be cardboard, we have the thickness, the length, all that, we have that done. So we're going to be adding a centering ring here. Okay, close that there, with it being a wood component, thickness of 1/4 inch, and of which birch. And then we have our automatically calculated the outer diameter and inner diameter. So we're going to be bringing this to -9, just to allow us to use that full length of the fin tab. And then a nice thing with OpenRocket, if you Control-C, Control-V on any highlighted part, it copies it. And we'll be bringing this up to, I'm going to say, back 1/2 inch to account for the motor retainer and anything like that. So itself is there, and then a mass component for the retaining hardware, which is the eye bolt and the quick link. So we'll be moving this up to that first centering ring, as well as adding a mass component for the adapter. So that is 130 grams, and you'll only need this for adapting from a 38mm motor to a 54 motor tube. So I'm going to move this up to right behind the aft centering ring, and we have 130 grams. And then we'll be adding the parachute, of which the current parachute is a 3-foot diameter canopy, and the lines are 24 inches long. For the deployment of this, we want this to be at apogee. If you have a flight computer or any electronics like that, you can have a specific altitude for deployment, or seconds after time. So, but with this being a dummy class rocket, not having any electronics in it, it will be at apogee. The packing size of this is about 3 inches by 2 inches, and then after that we'll go into the shock cord, which is, well, like I said, holds everything together. We're going to have a 10-foot length shock cord, and that packing length is about 2 inches by 2 inches. That is 22. Okay. And then I'll be moving this just aft of the parachute. And now that is the internal components of this completed. We'll move on to fins in a second. Well, main thing we'll be looking at when we're designing our fins is the stability, with the fins and nose cone being the biggest things you guys can customize of your external rocket appearance other than the paint job. So this rocket is going to have 3 fins. It's up to you. I would recommend not more than 5. 3 to 4 is the common recommending. I usually go with 3 fins. But we're looking at the stability ratio here. We want that to be between 1 and 2. If it's over 2, it's overstable. That itself is not anything wrong, but it's something that we have to keep an eye on. As well as if we have under 1, that's something we really do not want. So we want that between 1 and 2. I like to have that in the 1.25-ish range. But before we go into the motors, we're going to jump to motor configurations, where we're going to click the inner tube and add new component. So now we can select a motor out of the database to put in. So when we fly a level 1 cert, we use H100s, which is sold by a few companies, but we go with Aerotech right here. And then that will be giving us some initial stability stuff where we can start our stability with our fins. So this is, again, without a payload section in our payload, a payload in our payload section, so we're not accounting for that stability. It would be the same thing. You want to look at your stability ratio. You want that between 1 and 2. So now with that complete, we can go to our freeform fins. This just gives you more customizability with that. The main restriction on this is we don't want pointy edges, which I can demonstrate in a second, but as well as we don't want to have a thickness of, we don't want size of fin bigger than 15 by 15 inches due to our laser cutters size. So I'm gonna have very small fillets. I'm talking 1/4 inch fillets. I'm just gonna use that with my finger, so I have my glove and then run it along the root cord. I do not believe epoxy is here. If you don't have it there, you would have to make a custom, and the current weight of this is 0.751 ounces per cubic inch. And then with that, we can start making our fin shape. So I'm going to make this probably a 9.5 inch length fin. So I'm going to bring this back to here, and then I'm going to general bring it back to be 0. Oh, I did that. I'm going to make this 9.5 inch. Whoa, that is not on. So we're going to go to 9.5. Delete 9.5. There we go. Going down to general, I'm going to make that to be flush at the base. So on the back to the fin shape, bring this back over here, and then zoom out. I'm going to have this to be located at 7.5 inches, 7.5, and this to be at 10.5. And then I'm going to bring this out to be 2.5, whoa, 2.5, and then 2.5. Now, the main thing I'm looking at when I'm putting these numbers in is the stability margin right here. We want our CP to be behind our CG, which is shown right here, and then also visually on the rocket right here. So, you can drag these around, up to you, but I like to go just by this way of having 7.5, and just visually doing it like that. So I'm going to jump these to 3.5. Not actually typing in fully sometimes, so 3.5. So again, a little less, so I'm going to bump it up to 4. There we go. I like to have my stability ratio for subsonic flight around that 1.25 mark, but that is up to you between that 1 and 2 ratio. I would always recommend 1.25. Right now I'm sitting at 1.31, which is completely fine, and with a little bit of a basic fin shape, which I'm fine with. And then for the fin tabs, which actually connects the rocket fins to the substructure, we can do automatically calculate. When you do this, you want to make sure that you have the dimensions of the fin between the two centering rings. Now we did see that the stability decreased, so I'm going to go back to that fin shape, and I'm just going to make it a little. I'm going to make this 11. And I'll make this 7. A little more blunt, which will, there we go. I might jump this to 4.25. Okay, so now with that done, we have a fin design and an overall rocket design. Now, when you have a payload in your payload section, your fins won't need to be as big because that pulls the CG of the rocket forward. So, with me not having a payload in my payload section, that does bring the CG back, which itself needs to have a CP further back. So with this, it's also kind of future-proofing this rocket design to a L2 type-esque design. So we're just going to go back to fin tabs, make sure that's all good, which it is. And then now with that, I'll show you the motor for a L2 rocket, which will be, oh, one thing I did forget is the rail buttons here. We want these to be behind the centering rings here because we screw them into the structure, and it allows for the screws not to be caught on the payload. of the parachute or shock cord. So I like that there. I'm gonna copy it, paste it, and then just bring that down there. And this, like I said in the lab, this holds the rocket onto the launch stand. So with that, if you're looking at reusing this also for L2, for a new configuration, we'll look at a J250, which is what we used in the club for a DMS version. So that is not reusable. That's what we use in the club for level 2 certifications. So you can see that we did become unstable with that, just because that is a heavier type of motor and that pulls the CG back. So what we can do to fix that is adding a mass component into the payload section of actually having a payload. And let's say, I think my payload was about that 350 grams. So throw that in there. Oh, look at that. We are back to being stable. And that was around there. So, we're hitting that 1.25 ISK with that. So this rocket design can be used for L1 and L2, but make sure that your payload weight can account for that heavier weight of the booster. But we also look at it, we won't be needing the hardware to adapt. So we take that off, and we're back to being stable. So I'm going to Control Z that, delete this mass component because I am making this for a level 1 class rocket. So this is what we'll be using for our design. And with that said, we can start on the modeling section of the video. So on the computers in the NX, G400, and the computers in the lab, we will be using NX as our main software. So we'll just type in NX, it pops up right here. And what we want to do, we'll start off with the fins. So I'm going to take a screenshot. There we go. And that gives a shot for the, I'm going to see if that's saved. And it turns this, it did. So I'm just opening that to make sure I got everything on there, which I did. Lovely. So I'm going to type in OpenRocket NX. So it might be okay. NX. Open. There we go. So with the screenshot that we just took, we're going to use a thing called raster image, which is where we can input a file into a sketch, and then we can make the we sketch on that image to allow for it to be sketched onto our actual sketches for us to be using. So with that, there we go. I'm going to just click that up there. Okay, so with that, we're going to start a new file. Oh, that's open. Start a new file. I'm going to be using inches for this, and then this being fin, I'll label it as L1 fins. So now with the name of that, and we want to make sure that's on model and then inches, just because I've been using inches. And then now that it has popped up and everything is going good, it's still loading. Okay, so now we're ready to go. We're going to search on the top. I'm going to bring this down here for right now. We're going to type in raster image. That pops up right there. We want to open up the file, which is right here. Pictures, screenshots, JPEG. Oh, I did not save the file as JPEG. That's okay. I'm going to switch down to PNG. There we go. Okay, so we're going to open up that file. I'm going to select the plane down there. zoom in, and I'm fine with how that laid out. So I'm going to click OK. Click Sketch. We want to make sure we click the top-down version for when we're exporting this. So we click down on top view, and then now that we have the sketch here, we can just sketch along this, and we have our dimensions. So I'm going to take the line here, line up, I'm going to zoom in, take there, come over, line up there, take from there, down to here, and we'll be just tracing the outline of our rocket. So then there to there, there to down here. If you do want to be exact, you can be. You can get all the dimensions off of OpenRocket, but this will be just as good. It'll be slightly off just because of it being eyeballed. Now, we do have the ability, oh, come on. Oh, I'm going to cancel that. Bring that to right about there. And then continue sketching along the outside. About. I'm going to use this to sketch the below. And a line there. And then now it will line directly up to that section. And there we go. So now we have traced the outline of this fin. We're going to pop back into OpenRocket, go into the fin section, go to fin tabs. We look at our length right here. So I'm going to copy that length, jump back to NX, click on that dimension, double click, unhighlight, click there. There to get dimensions. Oh, double click. Click there. Paste in our dimension. And then we want to yes to scale the entire sketch. And then now that brings the entire shape of the fin there. And when we click enter on that, that will give this dimension a actual dimension. So you can change the size of these up here. I'm going to go back to home. We can look at this section here. This is supposed to be 4 inches based off the OpenRocket, and then go back to the OpenRocket. I don't have that memorized of the fin tab height. So I'm going to copy that, jump back over to NX, paste that in there, paste it back in here. Go. And then final thing we check with it being 4.5, we click here to here. That is pretty close to 4.5, so let's check 4.5. I'm going to not do that actually because that is close enough to what we wanted for dimensions. All I have to do is click around and give these all actual dimensions to make it a final sketch. Once we have that, we're going to click this point here as well as this point at the base, and then click the make coincident, which will just lock it together. And with that, there will be, oh, what I do? Oh yes, we want to have our length here given. Forgot those. And this will scale everything together so it brings everything over as once. So click there, back to that point, have it touch, align, there we go. Now we have fully defined sketch. We'll be finishing this, and then we can hide the screenshot. So now we're going to export this file down here at export, down to DXF. And then we're going to be, make sure it's DXF, to location, we're going to be going to downloads, and then that'll be fine though. So we'll go to next, to export view, we don't want walk view, we want to select a view, and of which it is top down. So we looked at it we made it from the top of the actual software, and we'll be making it from the top there. So I'm just going to pull this back up to here. We can actually look at it. Yes, so then we have next, 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 and we have that in the download. So we finished that. Yes, we want to save. And then now if we go to our fin tabs, back to here, we want to do not actually save to export DXF. Next, we want top down. Okay, never mind. It did work. It just took a second. So if we look back over here, we can see that we have our fin tabs, right? Our fin shapes right there. So now with that said, we can move on to the a new file to make the nose cone. So the nose cone itself will be more complicated just because we chose to be longer than 10 inches. I recommend staying at the 10 inches. Is significantly easier on the manufacturing process as well as the design aspect of that. Where again, we'll make this L1 nose cone. We're going to go back to OpenRocket, take a screenshot of the nose cone, and then the exact same thing. We're going to pop back down to hello, this is post Ben. I realized I did something wrong with the nose cone, so I'm going to be redoing that. But some updates from the future Ben of we're not having a actual certification video. So next video will be manufacturing, and in the beginning of manufacturing I'll be talking about the certification process a little bit instead of having a whole dedicated video towards that. But other than that, we're going to go back to NX here, make up a new file, and then start working on our nose cone. So just like with the fins, L1 nose cone, make sure in inches and model. And once that is up and running, jump into raster image. I'm going to find the file. There she is. And then specify the plane. I am choosing the ZY plane since that's the more accurate plane to put in, but does not really matter. And now that the raster image is there, we can go to sketch on the ZY plane, and then we can start sketching on there. So the mistake that I made on the other video, which you guys aren't going to see, I did a very simple mistake, and instead of just typing it out, I'm going to be doing this redo of the video, but of which I'll talk about where I messed up, of how I messed up when we get to that step. Make sure we outline all the outlines of the rocket, of the nose cone, and then when we get to here, when we get to the curve of the nose cone, we're going to go to arc, of which, click there, all the way up to here, make sure we're highlighting the whole part, and then line up with that nose cone. So what this is telling the computer is, okay, now keep that there. Now we're going to switch back to OpenRocket, get the total length of the, this is the length of the upper section here. So I'm going to copy that. Shoulder length is 3 inches, so it's going to be 15.375. Yep. Jump back to NX. Now with all of these parts connected to each other, just like what we did with the fins, we're going to scale the whole dimension, scale the whole sketch. So now with that, all these dimensions should be accurate. What I did on the previous attempt was I made this length 12 inches, which I believe on the updated version, with this computer not being updated, the only change is the updated version takes into account the length of the shoulder. So if you're using the updated version, keep that in mind. If you're using the old version, just keep in mind the total length of the nose cone. So with that, we should get accurate measurements for these, about 2 inches. That is correct. This is going to be 3 inches. And then this is going to be 1/16 of an inch. So 1 divided by 16. And our formula. And then we're going to make this into that radius. Now we're going to click this point down at the base. We'll click that one first, and then click the point up here, because that will tell the computer to move this first. Oh, I just did that point to that point, and I'm going to move that together. And now the sketch is fully defined, and now it's going to get to the little bit of a complicated part where I'm going to copy this, save out of the sketch, and then I'm just going to hide this. Is not really needed. And then go down to save as. I'm saving as the exact same thing under my downloads. Nose cone V1, and then save the exact same file but as V2 or however we want to name it. So now this is V2. So with the whole length of it being just shy of 16 inches, we have to make sure the two parts of the nose cone do not exceed the length of 10 inches. So how we're going to go about doing this is open up the sketch once again. This is a V2, so we'll be focusing on the upper section of the rocket. Well, we're just going to get a line straight across as our dividing line. This measurement is 8 inches, so I'm going to make that 8 inches. So that's the kind of halfway mark. I changed my mind. 8.5. Well, this, like I said, will be taking up upper level of which, so that leaves about 7 inches up here and up a 1 inch shoulder for the actual component. So we're going to get here to touch there, and then this length is going to be 0.1 inch. And then we're going to drop this down by 1 inch and then over to connect. So I'm going to leave this as not fully connecting just for this second. I'm going to bring that to 1 inch. And then what I'm going to do is click this extend feature up here to jump across, close, and then that will give this a final dimension of whatever that is. And then now that will go into actually looking and then deleting this bottom part which we don't need. So we use the trim function, just draw along here, erase all of that, and we're going to bring this corner all the way down to the center. Whoa, Control Z. We need to touch that up to there. And now with that, we can jump and bring this down here. And then bring that down. And now we have a fully constrained model for the upper level of the nose cone, and of which we're just going to finish. We're going to revolve. We want to make sure that we click the component, then the vector, so we want this up and down vector on the Z, and then specify the point that we're rotating around, so just click there, and there we go. So apply that, and then shell. We're going to shell by 0.2 of an inch right there, and then we're going to hide this sketch just so that it's easier to look at. But then we see the point of the nose cone coming together, and this we made 0.1 inches, then the other one would be 0.95 to account for tolerancing. And we're going to export this as a STL file. So just like with the actual NX files, so we're going to specify into where we want them, and then then we're going to highlight the object, click apply, and then with me looking into the download section, it is popped up in the download section. So now we can open up the V1, which is the exact same thing. Where we left off, jump back into here, and we made the line at 8.5, I'm confident in saying. 8.5, and then just to confirm that, here to the point, it was 7 plus bingo. So that is correct. And then we can just double check that real quick by going into here, jump into sketch, and then yes, so it was 8.5. Okay, so exact same thing, bring that over to here, have that to touch, shorten this to 0.95, whoa, sorry, 0.095, have that come down by an inch, and then over, and then we'll do the extend feature just like how we did before, this being 1 inch, extend, bingo, and then we want to label everything to make sure it is all accurate. So now with that, what we can do is specify that to there, and then finally we're going to that trim section and just drawing away all of that. Oh, and that point up there, we don't need that. So now we have the sketch fully defined once again. We're going to go back to the revolve feature, specify what we want to revolve with the object. There we go. Specify the vector again on the Z, and then specify the point that we want to spin around, which is just the head axis right there. Now with that, we can hide the sketch, go into the shell feature. We want to specify the top and the bottom for 0.2. And then with that, we have the lower section and the upper section finished. And what we'll do is we will save just like we did before as STL. So it specifies in the locations, bingo, and then the object we want to specify as this. I was okay with that, and then looking over, and there we go. Now we have the fins catted and exported to DXF, as well as the STL files exported to STF. So with that, we'll give those to the actual RSO, and they will get it queued up, and that will be everything that you need to make for your components. Now, if you want to, I'll go into depth with that as well, up to you. but we'll make the coupler and the coupler, bulkhead, and center rings. It'll be the exact same process as we just went through with the two wooden components, the bulkhead and the coupler being for the wood, so we'll export as DXF. But we do not need to do that for the certification process. The RSO board, the RSO officers, the execs, and all that, we have a predetermined measurements for all of that. But I'll be making a circle for a coupler for this with it to show you guys how to. So we have a base circle here, then we do an offset of 0.2 of an inch, and then this diameter, whoa, we do not want that. We want it to be 3.6, and that gives a total dimension of the exterior. Oh, we have not have that fully in the middle. Right. Connect, bingo. Now fully sketched before, and it's in the dimensions that we need. So now we're just going to extrude this by 6 inches. Done. And then I'm going to export this as a STL. Bingo. Ambo. I'm going to change the name of it to be L1 coupler. So one other thing to do this is to, if you want to have a full CAD model of that, it is not necessary to do that. I would recommend it just to get better with CAD. But that's all you need to make is the nose cone and the fins. Now, anything for the next video for manufacturing, I'll show a few videos of these be 3D printed or laser cutted, but for the manufacturing process individually, you'll give the file to the exec board or officer board, and they will get it laser cutted and 3D printed, and then you'll get the materials back when you come into the next build day or whenever it is done out of the queue, and then you start manufacturing. So only step that won't be referred to directly in this video is going to be directly giving the file to the RSO or anything like that. So the next step for you guys would be getting RSO approval, and that will be with them overlooking the open rocket to make sure everything's up to date, it's functional, it will work in flight, and then showing them these part files and making sure that all those are okay. And then when they give you a thumbs up, you can start manufacturing. So wish you guys the best of luck in this journey. It is a very rewarding process. I've loved it myself, but I'll see you guys in the next video with manufacturing. Thank you for coming along. It's been a long video, but I thought I went in depth, and make sure you guys get your dimensions checked by the updated dimension board. Again, disclaimer, this was made with measurements for the 2025-2026 school year. So keep that in mind. Wish you guys the best, and I'll see you guys in the next video. Thank you. Bye.